one of the things that bothers the system, and that is spots on the stars. They add noise to the system, and we can now distinguish from planets from spots on the stars. But that's still not the whole task. Having found these candidates from their transits, we still need to be sure there aren't other astrophysical phenomena that could provide a confounding signal. And so we have our science team of some 35 members who will be using many of the Earth's biggest ground-based telescopes to confirm these results. They'll be looking at the stars to see if maybe what we're seeing is a small star orbiting a big star. Maybe what we're seeing is next to our target star is another little star that's eclipsing. So they will go and make sure that it's not some astrophysical phenomenon, it really is a planet. And so at the end of the period of time of the mission, which is about 3 or 4 years, we should see 3 transits of these planets. We should have the confirming observations that we'll need, and then we'll be able to make our announcements. We're not going to be able to tell you very quickly whether or not there are Earths. We're going to have to wait until we see these 3 transits. But the team is extremely excited in getting started. Get the spacecraft up in orbit, get it calibrated, and let the data come down so we can actually start seeing these transits and start to answer the question, are Earths common or are they rare? Jim Fanson, the project manager, is here to tell us more about the mission. Jim?
Thank you, Bill. I'd like to describe some aspects of the spacecraft as well as the design of the mission. If we can have the next graphic. We start out showing you some footage of technicians working on the primary mirror of the telescope on Kepler. This is a 1.4 meter diameter mirror. The Kepler telescope, in order to monitor, simultaneously measure 100,000 stars, needs a very large field of view. So our field of view is about 30,000 times larger than the Hubble Space Telescope. Focuses the light on the focal plane array, which you just saw, which is the crown jewel of the vehicle. Here you see the solar panel being attached to the side of the vehicle. It provides about 1,000 watts of power and consists of about 10 square meters of collecting area. The vehicle was delivered for processing at the Cape, and here you see the entire completed vehicle. It's about 15 feet high, about 9 feet in diameter, weighs about 2,300 pounds. So the vehicle this morning was moved to the vicinity of the launch pad, and we're looking forward to a launch in early March. I'll walk you through the launch sequence on the next graphic. Here you see the launch of the Delta II rocket from Pad 17 at the Kennedy Space Center on the Air Force launch pad. We climb out over the Atlantic Ocean. About 5 minutes after launch, the fairing separates while the second stage is accelerating the vehicle. The second stage shuts down after about 10 minutes, and we're actually in a 100 nautical mile orbit around the Earth. We coast for about 43 minutes across the Atlantic and the Indian Ocean. And as we come across the western coast of Australia, the second stage engine reignites. It burns for another few minutes. We then spin up the third stage with the spacecraft on it, and the third stage burns for another few minutes, putting the vehicle into its final trajectory, leaving the Earth. At that point, we'll be traveling at about 6.6 miles per second, and the vehicle will be in what we call an Earth-trailing solar orbit, which is the same orbit that the Spitzer Space Telescope is in today. The next graphic gives you an illustration of how this orbit works. It's basically we trail the spacecraft out behind the Earth. It drifts behind the Earth about 1/10 of an astronomical unit, it's about 9 million miles per year. And as Bill said, we're pointing at one part of the sky, monitoring 100,000 stars. But because it's solar powered, this means that once a quarter we have to do a 90-degree turn of the vehicle to keep the solar panel pointed at the sun. So this is illustrated here in the graphic. The Kepler vehicle is really a marvel of engineering. The focal plane array, which, as Bill mentioned, is about a square foot of silicon. We have a full-scale mock-up here. It's the largest camera that we've ever flown in space. And this 1 cubic foot of spaceflight hardware contains more than 20,000 components. So it's the most complex piece of spaceflight hardware ever built by Ball Corporation. So we're very proud of the achievement, and we're looking forward tremendously to the science return. I want to emphasize that the vehicle was a very challenging technical achievement. In order to find these stars, we have to be able to measure the brightness change of stars down at the 20 part per million level. It's an extremely challenging measurement. It's akin to measuring a flea as it creeps across the headlight of an automobile at night. That's the level of precision that we have to achieve. So I'd like to turn it now over to Deborah Fisher. She'll talk to you a bit more about the science return we expect.
Right. So as someone who's actually external to the Kepler team, I'd like to first say that this is a historic and incredibly exciting event. I've worked on exoplanet discoveries for the last 12 years, picking off one by one some of the 300 and some known extrasolar planets that are found. And now we're going to have the opportunity to launch Kepler and to see the incredible results that will come in. The main difference between the types of planets that we're discovering with radial velocity technique that I use and the Kepler mission is that Kepler is really going to probe the habitable zone of planets. In the first graphic, in fact, I'd like to sort of explain a little bit about what this means for different types of stars. You can see three different types of stars from top to bottom, going from the hottest stars to the coolest stars. The hottest A-type stars, as they're called, are very luminous. They put out a lot of energy, and their habitable zone is actually much further away from the star than for our sun. Our sun, depicted in the middle, is a G-type star, and as you know, the habitable zone for a planet orbiting a star like the sun has a period of 1 year. And then finally, and perhaps most interesting for the Kepler mission, are the M dwarfs. These very low luminosity stars are not giving out as much energy. To be in the habitable zone around one of these low mass stars, you have to move in a little bit so you can warm up, basked in the starlight. And then the interesting thing is that because you've moved in, the orbital period, the time it takes to go around the star, is much shorter. And so what Kepler will be doing is watching as the planet goes across, blinks the starlight out, and with the M dwarfs, the frequency of the blinks of planets in the habitable zone is going to be much higher. They're going to see many more repetitions, and I think that's going to be quite exciting. What I'm hoping, expecting to see as a community scientist is that in the first 6 months to a year, the big, massive, hot Jupiters, as they're called, are going to roll out the Kepler assembly line. And this is exciting because these are bizarre planets. We don't really understand the statistics, how they form, how they moved into their current position, and just the sheer number of these objects that Kepler will find is going to help us learn a lot about the systems. We have also, NASA also has in space the Spitzer Space Telescope, which will be able to do follow-up, looking at the atmospheres of these hot Jupiters as they're found. And then the next class of planets, I think, that will roll out will be perhaps the hot Neptunes. Okay, significantly smaller than Jupiter. These objects are thought to exist around something like 30% of stars like our sun or low-mass stars. And if that's correct, then Kepler should see quite a few of these fairly large, something like 17 times the mass of the Earth, fairly large planets orbiting. And then the hardest detection, and by far the most exciting, is going to be the detection of bona fide Earths. Earth's small rocky planets, Earth-sized planets that orbit around other stars. And if we could show the next animation, which, often we think of these Earth-like planets as truly rocky worlds with solid surfaces. In fact, I think that the science fiction writers are going to be challenged to imagine the diversity that we could expect to find even in these types of planets. They may not be rocky worlds, they may be water worlds without plate tectonics that force the land mass up above the oceans. These could be worlds that in fact have life like our oceans, okay, but perhaps not sending radio signals to us. So I guess I'd like to conclude just by congratulating the team. They've done an amazing job. They've made it look easy, and we're all looking forward to the results in the coming months.
Thanks, Deborah. And with that, we'll move to the question and answer portion. Just for information, we're taking questions from the live studio here. We're also taking questions via telephone bridge and from NASA's centers. A caveat before we start, though.